What does this game and this game have in common with newspapers printed 100 years ago? The answer isn't just a piece of computer history, it's one of the most useful tools of graphic design. And today we're going to show you why some indie games are using this century-old technique to create compelling visuals. This is dithering, a technique that is not just about making things look retro, but about creating distinctive visual styles that could be impossible to achieve in any other way. And once you understand how it works, you can use it to create everything from a nostalgic look to unusual effects that will make your game stand out. Hi there, I'm Herman and this is Gamelogic FX. Like many of you, I've experimented hundreds of hours on Game FX, discovering new techniques that transform the way that our games look and feel. On this channel, we explore the world of Game FX, from classical techniques that are finding new life in modern games, to new approaches that can give your projects that extra touch of magic. So if you're ready to dive into the world of Game FX, hit subscribe and the notification bell. We've got some amazing techniques to share, starting with this video's exploration of dithering. Our springboard is Lucas Pope's game, Return of the Obra Dinn, released in 2018. That game is famous for its tricky logical puzzles and striking visual style based on two core rendering techniques, dithering and outlining. In this video, we will look at dithering, what dithering is, where it comes from, and why it's still relevant. By the end of this video, you'll have a solid grasp of dithering, from basic algorithm games used to coding them in shaders, and some unexpected non-visual uses. I'll show you what you need to start using these techniques in your own work. Have you ever noticed the dot patterns on old newspapers or the grainy look of early computer games? Dithering is the art of creating new colors by placing pixels of different colors next to each other in patterns, so that your brain perceives a blend. A simple example is this checkerboard pattern of black and white pixels, which at a certain viewing distance appears gray. This concept long predates computers. Artists have used dots or small marks to expand their color palettes for centuries. By around 1915, mechanized dithering known as halftoning was being used in printing, allowing newspapers and magazines to reproduce smooth-looking photographs in black and white using tiny ink dots. In all the computer displays that supported only a limited number of colors, dithering was essential. It enabled the developers to achieve the illusion of higher color fidelity by sacrificing some spatial resolution. Anti-aliasing is the opposite of this. It trades off colors to give the illusion of higher resolution. These two techniques are on opposite ends of the color depth resolution trade-off. And now, where our screens can display millions of colors, anti-aliasing is the more common technique. Even so, dithering remains valuable. It's key to many distinctive retro looks and can be pushed far beyond simple pixel patterns. In Return of the Obra Dinn, Lucas Pope used dithering to create a moody two-tone aesthetic that feels part illustration, part interactive fiction. In tiled games, dithering helps generate smoother blends between zones. It is still useful in specific cases where we may have limitations, such as to create transparency or shadows. You can use dithering patterns for entirely non-visual purposes, such as producing pseudo-random distributions with desirable properties, which we'll discuss a little bit later. Let's outline how to implement simple monochromatic dithering in a post-process shader. This requires 3 steps: converting the image to grayscale, then quantizing it, and finally modifying the image we quantize to get the dithered result. We will be using an unlit shader for this. Because I had to implement a lot of post-process shaders for this video, I wrote a script that allows you to connect the shader and any properties it may need directly in the inspector. Normally, you will need only one post-process shader, so you will not need a generic solution to hook up your shader and shader properties. To work with a single color, we need to convert the image to a grayscale image. To convert the scene to grayscale, we take the color RGB of each pixel and do a dot product with something like this. Look for the link in the description for more about this particular vector, which matches human visual perception of each color channel's contribution to a pixel's overall brightness quite well. By doing this dot product calculation, we get a single brightness value. To quantize something means to convert a continuous range of values into a smaller set of discrete values, essentially rounding values to fit into predefined buckets or levels. For example, we take the values from the previous step and round them to a specific one of only 4 values. The simplest quantization operation is to turn the floating point values into either 0 or 1, black or white. We use a threshold to decide everything above the threshold is white, and everything below the threshold is black. This technique is called thresholding. We can also do this with the step function. For example, if the value minus the threshold gives us a positive result, output 1. If the value minus the threshold equals a negative result, output 0. So this binary quantization snaps everything below a chosen level to black and everything above it to white. If we want more values than just black and white, we can introduce the level count. That lumps brightness into discrete bands. Any input value gets snapped to the nearest level that's less than or equal to it. It's like creating a staircase where each continuous value falls onto the nearest step below it. Another method is using a ramp texture. You sample the ramp at the x-coordinate equal to the value you want to quantize, and the y-coordinate equal to 1/2 or 0.5. There are two basic types of dithering. Order dithering adds a fixed pattern to the image. The nature of the pattern determines how the dithered result looks, and is the technique we will be focusing on. Error diffusion adds a value to compensate for the error as it processes pixels. We will discuss this technique when we look at one-dimensional dithering. In order dithering, we add a dither pattern to the image before quantizing. We start with our original value at the pixel, add some pattern that corresponds to that pixel location, and then we quantize this combined value. So quantization happens after applying the dithering noise pattern. Three types of dithering patterns are common: noise patterns, threshold matrices, and custom patterns. We will look at examples of each. White noise is the easiest pattern to apply. Although it kind of works, there are clumps and the overall effect is messy. Here's how it looks with a ramp, and here is how it looks on a sample scene. Blue noise is white noise passed through a high-pass filter. Because lower frequencies are damped, there is less clumping. The result is still random looking, but much neater. In the notes I will add links to more detailed explanation and blue noise texture downloads. Our noise pattern doesn't need to be the full size of our source image. We can repeat the pattern. One very useful feature of blue noise is that it's more difficult to see the repeating patterns that would distract the eye. We can also use handpicked values for our dithering pattern, called a threshold matrix. The best known example of this is called Bayer dithering. If you've seen old computer graphics, you might recognize these patterns. These matrices come in different sizes, using sizes and powers of 2, like 2x2, 4x4, 8x8. Each bigger size lets us show more levels of gray. There's a link to the formula you can use to calculate them in the notes. To make this work, we need to know which pixel we are working with. In the shader, we do not have access to real pixels, so we define our own pixel size and calculate the pixel coordinates from the UV coordinate. We will typically make the pixel size bigger than real pixels, so the effect is easier to see. For each pixel, we look up a number from our Bayer matrix. This matrix is arranged so that as the image gets darker or lighter, it creates clean, regular patterns. Here's how it works. We have our original value at each pixel of the image. We look up an offset value from a matrix based on the pixel's 2D position. We add this offset before quantizing. This is what it looks like in code. The mod operator used here effectively wraps our pixel coordinates to repeat the pattern of the threshold matrix. We do not need to do these calculations ourselves if the dithering pattern is an image, such as the noise patterns we looked at earlier, as long as the image wrap mode is set to repeat. Here is how the effect looks on a ramp, and here is how it looks on our sample scene. Different threshold matrices give us different results. For example, this matrix has been derived from the Bayer matrix, but with all the values in a single row. This gives us a very attractive line dithering. We can also use our own dithering patterns to create specific effects. For example, this uses a dithering pattern to create light and dark dots. And this pattern gives us a line effect. But unlike the lines created with the matrix before, the lines go between thick and thin smoothly. A more advanced twist on order dithering is to displace the dithering pattern lookup. For example, we can offset each pixel's horizontal position by adding its vertical position, while keeping the vertical position unchanged. This effectively turns the dithering pattern into diagonal lines. Or we can apply a sine wave to displace the pattern. Or we can tie the displacement to other attributes like brightness. There are lots of creative possibilities. We can get really pleasing results when we use anti-alias patterns like these. You don't have to use the same dithering method everywhere in your scene. In Return of the Obra Dinn, Lucas Pope used two separate dithering techniques: ordered Bayer matrix dithering for important foreground objects and blue noise dithering for the rest. Instead of dithering the whole screen at once, you can dither each 3D object separately. This means the dithering pattern follows the object texture coordinates. Each object can have its own unique pattern, and the results often look more artistic. The downside is that it's more complicated to set up because you usually need to handle lighting and shadows yourself. Here is a clever way to combine per object dithering and post-process dithering effects. In your object shaders, put different information in each of the color channels. In the red channel, store the lightness, and in the green and blue channel, store the texture coordinates. In the post-process step, the red channel value determines each pixel's brightness level, and the UV coordinates stored in the green and blue channels tell us where to sample the dithering pattern for that pixel. Here's how it looks with a few different dithering patterns. One challenge with this, however, is that it can shimmer when the camera moves. This can be distracting, like in this example. Lucas Pope solved this in Return of the Obra Dinn by placing the camera inside a virtual sphere that moves but not rotates with the camera, and projecting the dithering pattern onto the sphere. This way, when the player looks around, the dithering pattern stays consistent relative to their view. While it took him some time to get the tiling of the pattern of the sphere just right, and it's not perfect, it works quite well for the game. I didn't try this method. Instead, a simpler approach is to move the UV offset and rotation of the dithering pattern based on how the camera rotates. We calculate the UV offset from the camera's rotation on the X and Y axis, and the UV rotation from the camera rotation on the Z axis. Moving the texture with the camera works especially well in games like Return of the Obra Dinn, where mostly just the player's camera moves around a fairly static world. Until now, we've only been dithering based on the luminosity of pixels. However, we can also dither each color channel separately. This allows us to match the colors of the original scene, and we can also create some interesting visual effects. Here are some creative things we can do with color dithering. We can combine the color channels in different ways. We can use different patterns for each channel. We can create custom color ramps for each channel. Instead of settling for the run-of-the-mill RGB look, we can create distinct visual styles with the flexibility that this gives us. Ordered dithering is easy to implement in shaders. However, there's another type of dithering called error diffusion that gives even more pleasing results than the other techniques. But that is much more tricky to implement in real-time shaders because it needs to process pixels in each frame of the scene sequentially. So for visual effects, game often use other dithering methods. Because of its limited use in game visual effects, we won't discuss 2D error diffusion in this video. However, 1D error diffusion is actually used in many other non-visual ways in games, especially for creating well-distributed sequences of events, actions, and decisions. We use dithering for more than just graphics. In one dimension, it's handy for controlling random actions, like loot drops and spawn intervals, so you avoid huge gaps or big clumps, which can give the player the appearance of unfairness since it does not correspond to their intuitions of how random numbers work. As we mentioned, 1D error diffusion comes in really handy here. Let's say we have a sequence of values that we want to quantize. Instead of just quantizing each value directly, we keep track of our errors and add them to the values before we quantize them. Let's see what happens with a sequence of values all equal to 0.5. After error diffusion, we get this sequence of values, which basically alternates between 1s and 0s. Error diffusion with a sequence of 0.25 gives us this. We can make this even better by spreading the error over multiple values. This is why it's called error diffusion. We are spreading or diffusing the error across multiple samples. Different weights will give us different patterns. Error diffusion can easily be adopted to 2D, but as I've said, it's not easy to use in the shader. Ordered dithering also works well in 1D to help with non-visual aspects of a game. As with images, you can use a noise pattern, a 1D Bayer matrix, or a custom pattern, with subtle differences in how they are perceived by the player. If we use the Bayer matrix, we get a very structured repeating sequence. If we use blue noise, we get a sequence that appears random, but avoids clumping and gaps. It is great when you want something to be random but feel fair. Here are just some examples of where 1D dithering techniques are useful. Choosing action intervals, for example for ambient sounds, blinking animations, and lighting flickers. Choosing spawning intervals, such as for enemies, obstacles, and resources. Moving in discrete grids. Managing hit, success, or damage variance. Distributing order advantages in turn-based multiplayer games. And choosing NPC box. We can also use dithering for transparent objects, such as foliage, instead of using alpha blending. This results in much better performance when we have lots of overlapping objects, and it avoids issues with ordering of transparent objects. Dithering also has been used to create soft shadows where bilinear sampling is not available. Dithering is also used in certain volumetric effects to reduce banding. When you first start implementing dithering, it's easier to begin with a square screen resolution. While your final goal might be to support all kinds of resolutions, getting the calculations right is tricky. There are many decisions and trade-offs to consider. Focus on making the technique work first and add support for arbitrary resolutions later. And remember to make sure you're viewing the game at a scale of 1 so that scaling does not introduce artifacts that will mislead you. Make it easy to test your dithering on intensity ramps. This will make it easier to spot artifacts and give you better clues about what might be causing them. For color dithering, test on channel ramps as well as the hue lightness ramp. When you're working with textures for color ramps and dither patterns, you need to think carefully about several things. For sampling, you'll generally want point sampling when creating pixel perfect effects or strict color quantization. However, if you're going for more artistic effects, you might want to try bilinear sampling for your dithering patterns, especially if you want to create anti-alias patterns. The wrapping mode is also important. Color ramps should be clamped. If they're not, you'll get artifacts that are hard to track down. The same goes for full screen dithering patterns. They should be clamped too. However, if you're using smaller repeating patterns, you'll want to set them to repeat. As for mip-maps, you'll usually want to avoid them for basic dithering, though some advanced techniques use them creatively. When you're working with color dithering, while it's possible to put different grayscale patterns into the red, green and blue channels of a single texture, it's usually better to keep them separate while you're developing. This makes everything easier to control and debug, and it's simpler to experiment with different versions. Once you've got everything looking exactly the way you want, you can always combine the textures later as an optimization step. Consider creating your ramps and certain types of dither patterns procedurally. If you're using Unity, I've developed a tool which I've provided for you on GitHub that can help with this process. If you reduce your scene to a single lightness value, how the scene is lit makes a big difference to how easy it is to see what's going on. One thing that can help is to make the faces parallel to the viewing direction slightly lighter. This will lighten the edges and make it easier to see individual objects. You can also use outlines effectively to make the scene more readable, but we'll cover that in another video. And remember that you can cheat. When you're not actually limited by color depth, there is no reason not to use intermediate colors if they can improve the effect. We've done that to create the engraving effect, and even in Return of the Obra Dinn, there are more than just the two colors. Dithering may date back over a century in its printing form, but I hope I've showed you that it's still a useful and interesting technique today. If you experiment with any of these techniques, layer dithering, noise-based screening, or error diffusion, please share your results in the comments. In the description, I'll put links to example code, Unity tool for making ramps, Blue Noise downloads, and other resources you can investigate. Don't forget to like this video and subscribe if you want more deep dives into technical and artistic game effects. Oh, and remember to hit that notification bell so that you don't miss the next video. Thanks for watching. I'm Herman for Gamelogic FX. See you next time and happy dithering.